Welcome. Thank you. Sorry I'm late, and then I have to do the setup. Are those on Zoom? Can you hear me and can you see the screen? Yes, you can see this. Can you see my screen full screen or like? Last time we were doing this exercise and there was maybe a bit of confusion between the different methods to solve this exercise. So just to remind you the context, we were talking about estimation. How do we estimate parameters? Seeing as when we do stats, we have a population, which we are trying to describe, on which we do make hypotheses, and we only have a sample available. So I should go back even further. So this is the initial situation, okay? A population, and we only have a sample on which we can do measurements and observations. And so, because we only have a sample, we need to work out how we can estimate the unknown parameters of the population. So we said we can either have just a single estimated mean, but then we know there are several if we're talking about the mean, but it's the same for variance or proportion. But then we know there are several possible means, and so how do these different means from different samples relate to the real mean? And so we said instead of doing point estimates, we can use confidence intervals. And we were just working out what confidence intervals were. Someone has got their microphone on in the Zoom session. Can you see do you have a question? So, yeah, so these are confidence intervals, and the idea of a confidence interval is instead of giving a point estimate, which is this, it gives an interval which has a 95% a priori probability of containing the real value. So 95%, it could be, you can change the percentage of the interval, it can be 99%, but in that case it will be wider, as we'll see later. But 95%, if you want to understand what that means, it means that if you had 100 samples and calculated the estimate and the associated confidence interval, then of 100 samples, 95 of them would contain the real value of the mean, and 5 of them out of 100 would not contain the real value of the mean. Okay, that's what 95% means. And the percentage depends on the value of the error which we choose, like in a test. So if we choose 5% error, then we have a 95% confidence interval. If we choose 1%, we have a 99% confidence interval. If we choose 10, etc. But you have to realize that the larger the percentage, the wider the interval. So it's less precise. So you have to choose between the two. And so we looked at this introductory exercise where, just to remind you, the question was, we have a population of 30% of non-smokers. A random sample of 100 individuals is drawn in that population. And we worked out what the probability that the number of non-smokers was to be between 35 and 40, greater than 40, etc. And then we looked at how to find an interval which contains the observed number of non-smokers in 95% of samples. And so I told you that because of the properties of the binomial distribution, which is what the number of non-smokers follows, we can go from a binomial to a normal distribution. So we have the distribution of X, the number of non-smokers, can be considered to follow a normal distribution. Okay, so we'll write it up there. X follows a normal distribution with mean n times pi, so the number of individuals times pi, so that's 30. N pi. And the variance, n pi 1 minus pi, so that is 21, if I'm not. No, not variance, sorry, that is the variance. So, yeah, that's the standard deviation is the square root of that. So because we know this follows a normal distribution, then because of the property we saw several times before, we can deduce that Z follows a normal distribution with, we can do X minus 30, sorry, Z equals X minus 30 over square root of 21 follows a normal distribution O1. Okay, that's what we saw for all normal distributions. So when we say what is the probability that the number of non-smokers is greater than 40, we can use the probability that X is greater than 40 and bring it back to a standard normal distribution and then use the tables that we saw last time to find that probability. Okay, now we did that also for the interval. And then I just want to get back to this question because maybe there's a bit of confusion. Find an interval which contains the observed number of non-smokers in 95% of samples. So we're looking for an interval which contains the number of non-smokers in 95% of samples. Okay, and what I said is we can, so this is the normal distribution of X, so it's centered on the mean mu, and we're looking for A, B, such that this is equal to 95%. Okay? Now, I said 95% could be anywhere. It could be like this, okay? Then what's the total area under the curve, under a probability density curve? We saw that last time. What's the total area under the curve? 1, okay? Or 100% if we're talking in percentage. Okay, so maybe I should write 0.95, okay? So if we, several ways of having 95%. If we want it to be symmetrical, we can decide that we will look at mu minus C, mu plus C. So where this is C, okay? Now, so that was what I wrote here. So we decide we're going to look at the symmetrical interval. So there are different ways of doing it. Either we decide, remember that we have the table for Z, okay, for the standard normal distribution. We know that for the standard normal distribution, so Z, centered on 0, we know how to find the values of the probabilities. Do you remember that? We learned about that last time. So for a standard normal distribution, we know how to find the probabilities, so we could find the values here. So if you were looking at the standard normal distribution, or at this distribution, do you remember what we said that you had to remember about the normal distribution, about the percentages? Do you remember we said this percentage is between -1 standard deviation and +1 standard deviation. This percentage is between -2 and +2 standard deviations. Do you remember that or not? I said you needed to know that. So what percentage of values for any normal distribution is between -sigma and +sigma? Do you remember that? Well, à peu près, approximately 68%. Okay? So here, about 68. And then what percentage is between -2 standard deviations and +2? Do you remember? Yes. This, we remember that we said between -2 and +2, so all this is 95%. So that is what we want, which means that you could just say, without doing any other calculation, I know that between -2 standard deviations and +2 standard deviations of the mean is 95%, okay? Now, that means that this is the same as saying mu -2 sigma, mu +2 sigma equals 0.95, which means that C is equal to what? 2 sigma, okay? And so that means that because we know that sigma is the square root twice. So what's that? So square root of 21, because 21 is the variance, okay? Ça c'est la variance, ça c'est la moyenne. So can someone calculate that? Square root of 21? Oui, donc 2 fois 4,5. Voilà. Environ about 9, okay, we will say, okay. So that means that we can say P of X between, so mu is equal to 30, so 30 minus 9 and 30 plus 9 equals 0.95. So that means between 21 and 39. So we can write that back on the board here. For our case here, it is 21 That's the mean, 30 and 39. So the number of non-smokers is between, in a sample where there is 30% of smokers, the number of non-smokers is between 21 and 39 in 95% of samples. Is that, does everyone understand the reasoning? Yes or no? Yeah? Now, you might wonder, where does this 2 come from? So just to remind you that it's the 2 is because we had 196, okay? So it's an approximation of 196. So if we go back to this table, you can see that if we look for 196 here, that is equal to a percentage of 2.5%. It means if Z is greater than 196, here, 196, that is 2.5%, okay? So that's the same, because it's symmetrical, then if Z is less than 196, that is 2.5. So we do have that this whole zone is 95%, okay? So when we say 2 or 1, it's an approximation. 2 is this, okay? That's where the 2 comes from, okay? Do you understand? It's actually 196, it's an approximation of 2. So that's what we remember. About 95% of the values are between -2 and +2 for a standard normal distribution, and between -2 sigma and 2 sigma for any normal distribution, okay? So this is something you need to be able to do, because it's a way of finding probability. Now in the course here, so this way of doing is just using what you remember, or I mean what I taught you last time about the fact that 95% of values for any normal distribution are between -1.96 sigma or -2 sigma and +2 sigma. But another way of doing it is just to use the formula and to say, okay, so more like we did last time. Okay, so here I just did, do you remember how you go from X to Z? Is you go minus mu divided by sigma. That's always true. So if I just do the calculations, I don't do it that way, I do it this way. So I say mu minus C minus mu, moins mu, divided by sigma. So mu minus mu goes away. So there's just minus C over sigma. And then mu plus mu C minus mu is C divided by sigma is there. Okay, everyone understand how we go from there to there? We just do minus mu over sigma, minus mu over sigma. So here is Z, and this is that, and this is that. Okay, so there we've just continued the equation. And then we say, how do I find the probability that Z is between minus C over sigma and C over sigma? 95%. So I say that means the absolute value of sigma is less than C over sigma. So here I'm in Z. Okay. So I'm saying this is minus C over sigma, D over sigma, and I need to go to the table to find what this is, if this has to be 95%. So if you look at that, we're saying this has to be 95%. So that means this is 2.5, this is 2.5. So I will go and find the table, and I will say, if P of Z greater than C over sigma is 0.025, what is C over sigma? I'm looking for this. So I go in the table. I go in the table, which is there. And I say, what is the value? 0.025. This is the value, it's 1.96. So This means that C over sigma equals 1.96, or you could say nearly 2. C over sigma is nearly 2. And so then you just come back to the same reasoning as before. Okay, so that means C over sigma is 1.96. C is 1.96 sigma. C is 1.96 times square root of 21, which is 9. So it's a different way of reasoning, but it's the same result. Do you understand? Yeah? So then we get the same result. And the main point of this exercise is to say that you have constructed a confidence interval, because we say in 95% of samples, the number of non-smokers is between 21 and 39. So that's the definition of a confidence interval. So now, fairly quickly, I'm just going to give you the formulae for the confidence intervals of different parameters. So if I show you just the last slide, each parameter, so up there we have percentages, or means, or variances, donc les pourcentages, les moyennes ou les variances. Every type of parameter has a different formula for the confidence interval, okay? And the way they are constructed, we're not going to, yes?
Sur le diapo de la 18, il me semble, vous avez marqué que le C c'est égal à 9. Est-ce que le 9 du diapo, c'est le même que le C qu'on a trouvé là?
Oui.
Mais
ici, là?
Oui, mais le sigma, c'est égal à 21.
Racine de 21. Parce que c'est sigma carré, c'est la variance, est égal à n pi fois 1 moins pi.
Mais alors, pourquoi ici on a pris la valeur de 1,96 et sur le tableau de 2 alors?
Oui, because je vous ai dit, 2, c'est une approximation, c'est à peu près 1,96.
Le 2 qui est là,
oui,
c'est pas le 2 sigma sur la gaussienne.
Ben si, enfin, c'est l'arrondi de 2. Ça, c'est l'arrondi d'1,96. Quand je dis 2 sigma, ça, c'est aussi une approximation. En fait, c'est 1,96 sigma.
Ok, je vois.
Donc, en fait, when you remember it as a general rule, on dit, pour aller vite, on dit à 1 écart type, c'est ça, à 2 écarts types, c'est ça, et des fois, on dit même à 3 écarts types. Mais le 1, 2, 3, en fait, c'est des approximations. C'est 1,96, voilà. D'accord? Donc, c'est la même chose.
Ok, merci.
Okay? So I'm just showing you that there are formula for all the parameters. You don't need to know all the formula off by heart, because you will, in my course, you will be able to have at the exam a sheet of paper with the different formulas. So you don't need to learn them off by heart. What we did in the exercise, I wanted you to see where the formula come from. Where do they come from? They come from probability distribution functions and tables, and that's how you find them. So for instance, if we're looking for the confidence interval of a mean, la moyenne, for large samples, then using different theorems, we can show that the observed mean, m, and variance sig s squared. So we have x is a random variable with mean mu and variance sigma squared in the population. We draw a sample of size n with observed mean m and variance s squared using the central limit theorem, which is a mathematical theorem, which we talked about earlier. If n is a large sample, greater than 30, then we can say that this mean follows a normal distribution. Now be careful. Do you know why the mean follows a distribution? Why isn't it just a number? Why do we say the mean follows a normal distribution? You know that? When you have a population and it says we draw a sample of n, how many samples of n can you draw from a population? Many, many, okay? An infinity of samples. So when you say m is in fact not a number, m, it's the value of the mean in each different sample. So it becomes a random variable. That's very important. Donc, je répète en français parce que c'est important, on va s'en servir après. On parle d'une variable qui, dans une population, a une certaine moyenne, une certaine variance. La population, c'est toujours ce truc très grand et infini qu'on n'a pas. On va prendre un échantillon de taille petit n, donc admettons de taille 100, dans cette population. Mais quand on dit « je prends un échantillon », j'aurais pu en prendre plein d'autres, une infinité d'autres échantillons, d'accord? À chaque échantillon que je prends, je peux calculer la moyenne sur cet échantillon. Donc là, j'ai une moyenne, là, j'ai une moyenne, là, j'ai une moyenne, là, j'ai une moyenne, là, j'ai une moyenne. Et donc, ici, petit m, c'est une variable, c'est pas 3,9, c'est la variable qui a pour valeur toutes les moyennes possibles de tous les échantillons que j'ai pris dans ma population. Vous comprenez ça? Donc, c'est bien une variable, ce petit m. Et sur un échantillon, bah, il a une valeur donnée. Mais quand on prend en compte la population et qu'on parle de ce petit m, on peut prendre une infinité d'échantillons, donc ça devient une variable. Et donc, ce petit m, il suit, on peut le démontrer mathématiquement, il suit une loi normale, centrée sur la vraie moyenne, mu, et de variance, la vraie variance divisée par n. D'accord? Donc ça, that's very important, okay? So now we have a distribution for the mean, the observed mean, and so we can do the same as usual. Since m follows a normal distribution, we can subtract the mean and divide by the square root of the variance, by the standard deviation, to get a standard normal distribution. And so then, using the same type of manipulation and calculation as we did in the exercise, but we won't do it again, this is the formula for the confidence interval of the real mean, okay? The real mean mu, so I can just explain here if you like. So we say the probability that this, which is, what is this? We call like m is like our x, okay? M is like our x, and so this is like what? What do we call it over here? That's right, someone said it? Z, okay? It's what we call the standard normal distribution, okay? So this is like our x, this is like our z, because we go m minus mu divided by standard normal standard deviation. That's a normal standard deviation, standard normal variable. And so here we can say that z is between minus z alpha sur 2, 1 minus alpha. So that means that instead of saying 95% minus 1.96, 1.96, you can take any alpha you like. This is a general formula. So if I take alpha equals 0.95 minus 1.96 or minus 2 plus 2. If I take 1%, then that's 0.99. And this is other numbers that we can look up in the table. So this is the general formula. And then what you do is you just change the formula to have the mu in the middle. So you see, you multiply by this, change it over, and this is what you get. And so this is an interval for the real mean based on the observed mean. And that's what we call the confidence interval of the mean. So, and when we have small samples, so less than 30, then we change it slightly because even if it's only valid if x follows a normal distribution, and then this formula follows a student distribution, which is not normal, but we also have the table for the student distribution. So it's a slightly different formula for the mean. So now I'm going to ask you to do an exercise. So if you can take some paper, and to do this exercise, you need to use one of those two formulas. Okay, so I'm just going to tell you what this is. So this is, can you tell me what this is? This is the observed mean in a sample. Z alpha sur 2, écoutez bien, ça, c'est ce qu'il y a écrit dans les tables de la loi normale centrée réduite, au milieu, là, c'est toutes les valeurs qu'il y a dans la table. Et le alpha, c'est selon ce qu'on prend comme 5%, 10%, etc. Ça, c'est la variance observée dans l'échantillon. Ça, c'est la taille de l'échantillon. And if you have to use the next one, then this is M. This is Tn minus 1 alpha sur 2. Ça, c'est la table de student. Et ça, c'est la variance et l'échantillon et la taille de l'échantillon. So, in this case, you can do the exercise using the first formula. So take a bit of time to read the question and then do the questions. So have you finished? No? So you want me to put so you need to use this formula, okay? The one in red at the bottom. So have you found the values? So has everyone finished? Can we have a look at the answers? So, a study is set up to compare sleep duration at night in two groups of patients treated with drugs A and B, respectively Group A and Group B. Sleep duration is measured in 90 randomly selected patients. So in Group A, we have 50 patients taking the drug A. Their mean duration of sleep is 8 hours and the variance is 1.1 hours squared. In the other group, 40 patients taking B, mean 8.8 hours, variance 1 hour. And we want to calculate the 95% confidence interval of the mean sleep duration with each drug. So we use the formula which I showed you before. And so we, so it's the mean, the observed mean, plus or minus Z alpha over 2, multiplied by the square root of variance squared over the size of the sample. So here, it's fairly easy. We just take mean 8 plus or minus. So the hardest thing was maybe finding Z alpha over 2. So alpha here is, so it's true I didn't say, you can use an alpha of 5%. And why do I write alpha over 2 like this? Because in the tables, so if we want a 95% confidence interval, so if we want a 95% confidence interval, that means that alpha is equal to 5%, okay? So alpha, 95% confidence interval. That means that alpha is equal to 5%. And so why do we look for Z alpha over 2? Why do we look for that? Because in the tables that you're given here, table only gives you, it only gives you one side of the confidence interval. You want to exclude alpha equals 5% on both sides, okay? So that means that because you want to exclude 2.5 and 2.5, 5% altogether, you look at just 2.5 on one side and then you realize it's symmetrical. So fact here, you have to look for, get used to going from this writing to this writing. It's 8 plus something, 8 minus. Sometimes we write 8 plus or minus, but then when you calculate first, can you hear me still in the Zoom? Hello, can you hear me? Can you see the board?
Yes, yes.
So, second question was, I think it's second question was, how many patients should have been included in group B in order to obtain a precision of the estimate of plus or minus 15 minutes with the same 5% significance level? Okay, so the same significance level, alpha equals 5%. How many patients do you need in precision of the estimate? So there we're talking, because here we're talking about estimating the real mean. So here we're saying the real mean of sleep duration in group A is between 7.7 and 8.3 hours. And here we're saying the real mean of sleep duration in group B is between 8.49 and 9.11. So what is the precision in this formula? What would you say gives? So this is an interval. This is the point mean, 8.8, and we're saying the interval between which the real mean is, it's between 8.49 and 9.11. So this is your interval. Does everyone understand that, same as usual, we're saying there's a population of patients taking B, a big population, all those who ever take B. The real mean sleep duration, we don't know. In our sample, the sleep duration is 8.8. And with the confidence interval, we can say the real sleep duration of the whole population of people who take drug B is between 8.5 and 9. Okay? You understand that? So now we're saying, okay, this is my interval. I would like the precision to be smaller. Okay? So what gives the precision in this formula? Or in this one, what is it that gives the precision of the estimate? Sorry? Oui, pas que. But, yeah, this whole part, yeah? So now you can try and answer this question. How many patients should have been included in group B? So you suppose that the variance, you are right that the variance could affect it, but if the variance stays the same, okay, the variance stays the same and you still want alpha equals 5%, how many patients do you need in group B, okay? So now you do question 2. So you just have to write down the formula and tweak it a little bit to find the result. Right, so have you managed to find the answer? Yeah? No? Someone managed to find the answer? You think you found?
Je pense 62.
Ok. Est-ce que tu peux venir écrire au tableau? Pour expliquer comment tu as trouvé le truc? Vous regardez si vous êtes d'accord.
Tu vas chercher des quoi?
Écrire assez gros pour qu'ils arrivent à lire. Les là, So, ok, tu peux expliquer, donc, en français c'est plus facile? Oui. Oui.
Il égale
1,96, ouais.
Donc, on trouvait la solution de cette équation.
Voilà.
Et n égale 61,5. Et cela ne peut pas être. Doit être
un nombre rond,
oui.
un chiffre rond. Oui. Voilà. Est-ce que vous avez, did you understand the, you can sit down if you want. Thank you. So, thank you. Donc, the precision, we want the precision to be plus or minus 15 minutes. So because everything is in hours, you have to put it back in hours. So the precision we said is this. this is the precision, and we want it to be equal to 15 minutes, which is a quarter of an hour, yes? 0.25 hours. And so here, you transform this to find the n because the variance hasn't changed, it's 1. This is 1.96, so you have to square everything. Does anyone need help to get from there to there? Or is that okay? You square everything, z squared, this goes 0.25 squared, so it's n equals z squared, s squared over 0.25 squared, so that's that, and that gives 61.5. Is that clear for everyone? Yeah? So then, and your colleague is right, if you find 61.5, you need to include a number of patients. If we include 61, that means the precision will be slightly worse, slightly greater, so you take the number above, so you know you will have at least a 15-minute precision. Okay, so if we wanted a better precision, we needed to include more patients, or as you said, we would want the variance to be smaller, but that we don't usually have control over the variance, you see. So last question, are the mean sleep durations significantly different between both groups of patients at the 5% significance level? So if you remember in the first question, we said the mean sleep duration, the real mean for the people taking drug A is between 7.7 and 8.3. And the mean sleep duration for people taking drug B is between 8.5 and 9.1. So what do you think the answer to question 3 is? What do you think the answer to question 3 is?
Est-ce que vous pouvez traduire en français, s'il vous plaît?
Donc, j'ai dit que ici, on a montré dans la première question que la vraie durée moyenne des patients du groupe qui prennent le médicament A, le somnifère A, c'est entre 7,7 et 8,3, puisque c'est la définition de l'intervalle de confiance, on est d'accord, hein? Ça nous donne l'intervalle dans lequel, à 95%, on est sûr que se trouve la vraie durée moyenne. Ici, avec une probabilité de 95%, la vraie durée moyenne de sommeil avec des gens qui prennent le médicament B, c'est entre 8,49 et 9,11. Et donc, la question 3, c'est est-ce que les durées moyennes de sommeil sont significativement différentes entre les deux groupes de patients au niveau de significativité de 5%? Alors, pourquoi? Why? You can say it in French.
There's no overlap.
Good. There's no overlap between the two intervals. If you draw these two intervals, okay, so this is where mu A is, and this is somewhere where mu B is, okay? Look over here. Okay, so the reason why we can say, now maybe some of you, all those of you who have already done statistical testing, maybe you are already thinking to yourself, well, to answer that question, I need to do a statistical test, right? And that is another way of answering the question. We will see that we can do a t-test, for instance, to compare the means. But when you use confidence intervals, the confidence interval also includes a 5% significance level, and it's also based on probability of distribution of a parameter. So it's equally, in a paper, if you're doing research later, it's equally valid to look at confidence intervals or to do a statistical test and give a p-value. It's equally valid because both, they're different methods, but they're both based on distributions, probability distributions of parameters, okay? So because this is a 95% confidence interval, and this is a 95% confidence interval, then you can say mu A is significantly different from mu B, so the mean sleep duration is significantly different between group A and group B at the 5% significance level. Does everyone understand? So it's the same validity as doing a statistical test. So now we're just going to go, are there any questions about that or not? No? Yes?
Est-ce que l'écart type nous donne une information sur le degré de significativité de différence entre les échantillons? Par exemple, si on a une valeur d'écart type, on n'a pas d'intervalle de confiance, on n'a pas calculé, mais on a la valeur d'écart type.
Oui.
Est-ce que ces écarts types-là, s'ils sont superposables, on a le droit de dire qu'il y a une différence négative entre les deux valeurs ou pas?
Alors, pas directement, mais c'est sûr que donc vous ne pouvez pas juste regarder les écarts types et dire comme il est grand ou plus grand, ça fait une différence. Parce qu'il y a aussi la distribution, le Z, etc. et la taille de l'échantillon qui joue. Voyez? La taille de l'échantillon joue sur le calcul. Donc, vous pouvez, mais ce qui est vrai, c'est que si vous avez if you know that in one group, il y a un écart type plus important que dans l'autre, par exemple, ça vous donne une information, mais plus sur l'estimation, c'est-à-dire la certitude des estimations. Et si l'écart type de 1 est trop grand, vous pouvez pas, ça veut dire que ça varie entre là, et là, ça varie entre là et là. Vous pouvez pas forcément même comparer les moyennes. Mais vous pouvez pas directement regarder les écarts types pour déduire s'ils sont significativement différents ou pas. D'accord? Mais ça joue. L'écart type, il joue. Okay, so now we're just going to finish with confidence intervals. So I'm not going to go into detail, but like I told you, please, for each type of parameter, you have both two types of formula, either large samples, which can mean, in the case of the mean and variance, it means 30, samples over 30. Has disappeared. Okay, something's wrong. Sorry. C'est moi qui peux. Ah, parce que c'est un écran touch screen, maybe. Non. Voilà. I will come back to my So just to show you that, so here, just to show you, so there are large samples, and this means greater than 30 for the mean and the variance. And in the case of percentages, it means you have to check whether the size of the sample times the value of the proportion which you find here is greater or equal than 5 in 4 different cases, okay? But anyway, you have formula for large samples, and then since the mathematical theorems which are underlying those formula are based on asymptotic properties, we also have different formula for small samples, so less than 30, with some conditions, and you can see that they use different probability density functions. So if you just want to write notes on your paper, this is the standard normal distribution. Z, c'est la loi normale centrée réduite. Ça veut dire on va chercher dans les tables des lois normales centrées réduites ces valeurs-là. Okay? And T is the student distribution. So in the tables, you can go on internet, on Moodle, I wrote a tableau statistique, so, and I showed you before, so we have tables for the standard normal distribution, we have tables for student distribution, and n-1 means that, for instance, if you have a group of 15, then you look at 14, okay, line, it's the degrees of freedom. And then you also have to look at the alpha, the same as decide if you're looking at a 95% or a 99% confidence interval. And here, chi-squared is from a chi-squared distribution, chi2, une distribution du chi2. So depending on the size of the sample and the parameter that you're interested in, the intervals are based on the different distributions, normal or chi-squared or student, okay? And up here, it's also the standard normal distribution. And so P0 is the proportion we're interested in. And so here I say you get an interval with a lower value and a higher value. P1, c'est when once you've calculated the interval, you've got a lower value and a higher value. And you have to check afterwards that the assumptions, ça c'est comme condition d'application, okay, assumptions are met. You check, you calculate that, and then you check that this is okay, and then that means you can use it. Okay, so that's what I want to tell you about confidence intervals. And now you can look at the sunset. No, now I'm going to talk to you about something else. So, so now we are going to get on to a very important bit of the course, which is the general principles of hypothesis testing. Okay. So, for those of you who were in the Masters 1 course, or for those of you who have already studied statistics, hopefully this will be familiar. But even for those who did the Masters 1 course, I think it's important that we go through this again, and it is in English. So for those of you who asked me, I did put the courses up in French also on Moodle, okay? I haven't put the videos up because it's quite complicated, and I think that the course director wanted to put these Zoom lessons up. So I'll wait to see if they do that. So, we're going to recall what the aims of hypothesis testing are, the main steps, and what a degree of significance, a p-value, is, type 1 and type 2 error, and statistical pattern. And then we'll do a little quiz to see if you can if you've remembered and understood everything I said. So this is the same as usual. Remember, so I say it a lot because it's important. Remember that in stats, we are asking questions and making hypotheses about a large population with unknown parameters, because we can't measure every characteristic of every individual in the population. We draw a random sample on which we do have every single characteristic that we're measuring on every individual. And we calculate observed parameters, and we make estimations, point estimates or confidence interval estimates. And then we use statistical testing to make inferences about the population and the parameters. Now, the main steps of statistical testing are these, and we're going to go through each step. So first, examine the question under study in order to correctly state the hypotheses. Then state the null and hypothesis, alternative hypothesis. We'll explain what that is. Choose a significance level. Determine which test to use. This is the hardest bit for you. Which test must I use? This is what I get questions from students. I get them writing to me and saying, please help me, which test should I use? And when you get to real data, and the distribution of the test statistic under the null hypothesis, calculate the observed value of the test statistic in the sample, conclude by rejecting or not rejecting H0 and give an interpretation of the statistical conclusion of the test. So who in this room has an idea of what all those steps are? Who has a good idea of what all those are? Who has a little idea of what all those steps are? I hope the M1 people do, because we taught you in the first sentence. So you have a small idea, yes, of what all those are? But you're okay with me explaining it again, yeah? To make sure that you know it. So again, we want to know if the sample is a reliable reflection of what is happening in the population. So we've talked about estimating parameters and using confidence intervals. And now we need to talk about how we can be sure that extrapolating from the sample to the population is correct. And this is what hypothesis testing allows us to do. It allows us to extrapolate the results observed on the samples to the populations from which they are drawn. So the hypotheses are always based on the exact but unknown parameters in the population, but the test calculations are based on the estimated and the known parameters from the samples, okay? So population is hypothesis, exact parameters. Samples is estimated parameters, observed parameters, and we do the test and the calculations on the samples. So I give an example here. The specifications for a certain drug state that each tablet should contain 2.5 grams of active substance. The quality manager at the production site of this drug wants to know whether the manufactured tablets contain the required amount of active substance. In order to test this hypothesis, he randomly draws a sample of 100 tablets and measures the active ingredient. The mean amount of active ingredient in the sample is 2.62 and with an estimated variance of 0.16. So the director of the site, he says the drug, it's what it says on the box, the drug should contain 2.5 grams of the active substance, okay? And when he wants to check that this is true, so his firm, his production site produces thousands and millions of tablets, okay? So he just takes a sample of 100 and he finds 2.62. So the question is 2.62 different from 2.5, what it says on the label? So yes, 2.62 is different from 2.5, but you know what that means. The idea is we know that every time we take a sample, we're going to get a slightly different mean. So what we want to know is, does this result contradict or not the theoretical value? We want to know whether the difference is significant. So the aim of hypothesis testing is always to determine whether the observed difference in the sample is due to sampling variability or to a true difference in the population. So the hypothesis is saying something about a property of the population with using parameters, and the test is the procedure we use to test this hypothesis. So we're going to start with each step, examine the question, state that, so first we examine the question under study, so that's what we've been looking at, what is it about? And now we need to state the null hypothesis and the alternative hypothesis and choose a significance level. So the null hypothesis, hypothèse nulle, is usually called H0 for everyone. And it's the assertion that the value of a parameter in one population is equal to either a reference value or the parameter in another population. So for our example, it would be, because we know that the drug is supposed to have 2.5 grams of active substance, we want to know whether the value in this production site, the real mean value of active substance, is equal to the reference value 2.5. So this is what is actually the mean in our production site, and we want to know if it's equal to 2.5. And the alternative hypothesis is usually called H1 or HA for alternative. It's a new hypothesis to describe reality if the null hypothesis is false. So there can be three possible alternative hypotheses. Either if mu is not equal to 2.5, the reference value, either it is just different and we don't know which side it is. So that's called a two-sided bilateral test, or it's less than 2.5 or greater than 2.5. Those two others are called one-sided unilateral tests. You can only choose one null hypothesis, and most often we choose the two-sided bilateral test. So very important, the hypotheses always concern the real values of the parameters. So here I'm talking about mu and not m, little m. And we always state the hypothesis before we look at the data. So now we need to say, okay, we've got a hypothesis, we have a problem, we know what we're trying to work out. We need to choose which test to use and find out what the distribution of the test statistic is under H0. So this is a graph which I will come back to, and I'm not going to go into detail now, but this is a decision tree of how to choose a test with the main simple test which you need to know about in this course, okay? So first, we always need to look at what type of data we're looking at. So here, do we have discrete data or continuous data? The quantity of active substance in a drug. Continuous, yeah, okay. Continuous data. And are we looking at an association, or are we looking at different groups? Are we looking at the mean? So this association is if we have two continuous variables which we are comparing. So here we only have one. So we're in the orange. And here we're looking at variances or means. Are we looking at variance or means? We're looking at means. Do we have one sample or two or more samples? One sample. So we're going to be looking at a one sample t-test or z-test. I didn't put the z-test here, but this is what we're going to be using. So we'll go over the different possibilities later, but basically you have to go through the graph and decide which part of this decision tree you're in. So once we know which test we're using, we do also know for a given statistical test, we know what should happen if the null hypothesis is true. So in mathematics, when you say under the null hypothesis, it's the same as saying if the null hypothesis is true. It's just a bit quicker. So if we say under H0, under the null hypothesis, so under H0 means if the null hypothesis is true. So tell me again, what's the null hypothesis for us? What are we trying to test? It says this.
Equals to 2.5.
The mean of all the pills that comes out of our sperm is equal to what it says on the box, which is 2.5, okay? So active substance. So if this is true, then the distribution of the random variable we're interested in, so for us it's the mean, should follow a certain distribution, okay? Follow a certain distribution means a normal distribution or a standard or t distribution or anything that looks like it. And so if we know this distribution, we can describe what we expect to observe if the null hypothesis is true. So here I'm telling you, or we looked and we said, okay, it could be a one sample t-test or z-test. So I didn't say it on the graph, but you can also use z-test. So for the moment we'll use z-test. So if the null hypothesis is true, we know that the mean quantity of active substance should follow a normal distribution with mean 2.5. So if that is true, it means that we should have approximately 2.5 of active substance. So this is what we expect. A distribution of the mean is centered around the theoretical value. But we know that if we take a difference, so maybe there'll be one sample with a mean of 2.5, but we found a sample with a mean of 2.62, okay? And there might be another sample with a lower mean. So because of sampling variations, the observed mean in a sample can take any value under the null hypothesis, but we know how it's supposed to be distributed. So I'm just going to remind you that when we say this, this red, it means that most values, this is the frequency of the observed value, okay? So here it means that most values are around here. And then here there are less values that are around there, less values, and here very few values that are around here, okay? Probability density function, that's what it means. So, because we know the distribution that it should take if the null hypothesis is true, we can calculate the probability that the mean should take a given value. So we can determine extreme values which are too far from the expected value that have low probability of being observed if the null hypothesis is true. So instead of using the mean itself, we will use a test statistic, which is a random variable based on the parameter of interest. So for us, it's the mean, whose distribution is known if the null hypothesis is true, and which will be used to determine whether we reject or not the null hypothesis. So in green, I am white, coming back to the examples, and the rest is more general. So here, under the null hypothesis, and because we have a large sample, the mean follows a normal distribution centered on the reference value, 2.5, with variance, observed variance over the size of the sample. So we can subtract the mean and divide like we've done lots of times, and it means that this Z follows a standard normal distribution. And this is what we call our test statistic, okay? We say, if it's true that the mean is 2.5, then we should see that the mean is distributed around 2.5 following a normal distribution, which means that this should follow a standard normal distribution. And these are random variables because of what I told you before, because there could be an infinity of samples. So now we need to calculate the observed value of the test statistic in our sample, because we said, if it's true, we should see this. Now we can look at our sample and see if it's true. So we're going to compare what we observe in our sample with what is expected under the null hypothesis, to see the credibility of the null hypothesis based on the observations in the sample. So we'll assess the probability under the null hypothesis of observing more extreme values than the observed values. So we said, if the null hypothesis is true, I'll stay here so that people can see, if the null hypothesis is true, then our mean on the random sample should be centered on 2.5, okay? And we're going to see where the one in our sample is. So we had 2.62, but okay? If the M is close to the expected value, so that means that the probability of seeing something bigger than M is large, then that means that we're close to what we expect, okay? But if we find something that is very far from what we expect, with a low probability of seeing something greater than this M, then we'll say, well, the sample doesn't seem to go with the null hypothesis, because the null hypothesis is what determines the distribution, okay? So, and do you know why we look at this probability, the area under the curve to be greater, rather than just the probability that X equals M? Do you know why we look at the area and not just the probability? Because when you have a continuous variable, you can't calculate it's equal to 0. So you have to look at the probability of being greater than, okay? So, but the main thing to remember is we want to know whether this M is close to the expected values around here, or if it's a long way away. So here, we know that this follows a standard normal distribution. We calculate the value of this test statistic in our sample. So M equals 2.62. The variance equals 16. So all these were written at the beginning here. In the exercise, we wrote here. So 2.62, variance 0.16, and 100 tablets. So we go back to this. We calculate, we calculate this and we find 3. Now, do you remember what we said at the beginning here? So now you've looked at it lots of times. So if we have a standard normal distribution, Z, you tell me what is this value? What is this value? What's the mean? For a standard normal distribution, what's this? No, this. I'm not looking at that, this. Dans une loi normale centrée réduite, c'est quoi la moyenne? 0, voilà. Après, on regardera là. What is this value correspond to? Hein? Moins 1,96 ou 2, ok? Environ 2, ok? Je vais faire this. 1,96. Now, we found here, what did we find? Non, le Z0, il vaut combien? Ici, le Z0, il vaut 3. Donc, il est par là, ok? So, do you think, so we are saying, if the null hypothesis is true, we expect Z0 to follow this normal distribution. So most often Z0 should be equal to what? 0 or autour de 0. These are the most frequent values, okay? So we should see values around here. 68% of the time we should see between -1 and 1. 95% of the time. So do you think that this value, so Z0, si H0 est vrai, this should follow a standard normal distribution. And we find a Z0 qui est égal à 3. So do you think that this is true?
No.
Probably not, okay? Because the value we find is a very improbable, it's not an impossible value, okay? C'est possible que Z0 soit égal à, dans une loi normale centrée réduite, c'est possible d'avoir 3. Mais c'est très, très rare, d'accord? C'est très peu probable, okay? So, then we are going to say, so yeah, the probability, you can calculate the probability. The probability of observing a value greater than 3 is 0,0013. So it's a very low probability, okay? So using the table of the standard normal distribution, we can find this probability, okay? I gave it to you, 0,013. So since P is very small, either H0 is false, because we say all the time, if H0 is true, if H0 is true. So since it seems very different, either H0 is false, or H0 is true, but the observed sample is made up of extreme values of the population. Okay, that's a possibility as well. So the example I give often to students is, imagine I tell you that the mean size of Université de Toulouse students is 1.68. Okay, I don't want to offend anyone, I'm quite tall. We say it's 1.68, the mean size of the students of Université de Toulouse. And I say to you, go and get a sample of students from, because there's 20,000 students, so you can't measure them all. Go and get a sample and test my hypothesis, okay? So she goes, she gets a sample, she comes back, she says, I found a mean of 2.01. So I say, are you sure? Did you get students from Université de Toulouse? Yes, yes. What did you do? I went to the cruise. I went at the, when they're coming out from eating their food, and I said, I measured them. So I said, yeah, that's a good idea, you know, the people going to eat, okay? But she found a size of 2.01. And so then we look a bit further and we see that she found students on a day when there was a basketball competition, okay? So they were all basketball players, so they were very tall. But they were students from Paul Sabatier. But if we use that data, we will reject the null hypothesis, and we will say the mean is not 168, okay? But she had a sample with extreme values. Those students are from Paul Sabatier, So they are valid values, but they're not representative, so that's something else. But okay, you can have a sample. My hypothesis was true, the mean size is 168, but there was an extreme findings. So what are we going to do? We need to choose a threshold, un seuil, d'accord, une limite, a threshold below which the probability is considered too small for the observation to be compatible with the null hypothesis. So we conclude by rejecting or not rejecting the null hypothesis. So we choose a threshold, un seuil, based on the risk alpha of falsely rejecting the null hypothesis and on the alternative hypothesis. So we will say, okay, maybe there are some basketball players, but I will say that if we are in the 5% most extreme values, I will consider that it is too small a probability. And so there is a risk. So 5% is I accept that I will get it wrong in 5% of the cases, okay? But I decide to exclude the most extreme 5%. So 2.5 here, 2.5 here. And that will give me the 1.96, which you know very well, okay? This value. So if the value that I find of Z0 is greater than 1.96, I will reject the null hypothesis. And if it is less than, en valeur absolue, 1.96, I will not reject the null hypothesis. And if it's over there in the negative values, I will reject as well. Now this is, you have to choose the significance level, okay? If I choose 5%, I choose to exclude the 5% most extreme values. I could choose to exclude the 1% most extreme values or the 10%, etc., okay? Now, that's one way of looking at it. Or we can also look at the p-value. So instead of looking, we say we reject the null hypothesis if x0, I changed the names here, it's like z0 is greater than the threshold value, and that will change for each test. But we can also look at the area under the curve here that is greater than the observed value, compared to the area under the curve, which was alpha, which we defined to start off with, okay? So it's equivalent to say, I reject the null hypothesis if the observed value is greater than the threshold, or the area under the curve, petit p, p-value, is less than alpha. And conversely, I do not reject the null hypothesis if this is less than the threshold, or the P, area under the curve, is greater than alpha. Donc là, je redis en français, c'est hyper important, c'est vrai pour tous les tests, donc il faut vraiment le comprendre. Mais attention, c'est pas dans le même sens. Donc tout le monde comprend bien que ici, c'est la valeur observée de la statistique de test. C'est celle que je calcule, enfin, que le logiciel calcule, hein, qui vous donne, qui est déterminée par le type de test, et donc c'est la distribution d'une certaine statistique de test. Donc ici, j'ai une valeur calculée obtenue sur l'échantillon. Je regarde où elle se situe soit par rapport à un seuil, soit, plus souvent d'ailleurs dans les logiciels, on compare la p-value, c'est-à-dire la probabilité d'être supérieure à cette valeur observée, à alpha, qui est le risque d'erreur. Donc pour l'instant, ne vous inquiétez pas du divisé par 2, c'est juste quand il y a deux côtés, mais de toute façon, c'est toujours comme ça quand on regarde un test, qu'il soit bilatéral ou unilatéral. À la fin, on regarde toujours P et alpha, ou la valeur observée avec le seuil. Mais faites attention, c'est l'égalité, enfin vous le voyez sur le schéma, vous comprenez que la probabilité d'être supérieure à ça, elle dépend de ça, d'accord? Et que le seuil, il dépend du alpha, parce que c'est comme ça qu'il est défini. On a dit, je veux rejeter les 5%, par exemple, les plus extrêmes. Mais donc, attention, ça, c'est dans le sens inverse. Je rejette l'hypothèse nulle, soit si la valeur x0 est supérieure au seuil, ou si le petit p est inférieur au alpha. Okay? Et à l'inverse, je ne rejette pas l'hypothèse nulle si le x0 en valeur absolue est inférieur au seuil, ou si le P, la p-value, est supérieure à alpha. C'est bon ça? Ça, il faut bien savoir le faire. And the best way, la meilleure manière de ne pas se tromper, c'est de refaire ce schéma. Sinon, vous me faites des micmacs, là, vous dites faut que la valeur observée soit inférieure à la p-value ou le alpha supérieur au seuil, enfin, vous mélangez tout. Faut faire le schéma, on se trompe pas. Okay? And then if there's only a unilateral alternative hypothesis, then it changes the threshold. Le seuil change quand on est sur une hypothèse alternative unilatérale, mais c'est le même principe. So the definition of the degree of significance is the p-value, degree of significance, p-value, degré de significativité, tout ça c'est la même chose. C'est la probabilité, the probability of obtaining a value of the test statistic which is greater, more extreme than the one observed in the sample if the null hypothesis is true. Okay? So this is how you write, but if you've understood this definition, then you're fine. It's just the written definition. So the smaller the p-value, the less the null hypothesis is credible, and we are more sure that we are right to reject the null hypothesis. Okay, do you understand this? If the p-value, if x0 is a long way over here, then I'm sure I'm right to reject the null hypothesis. The closer it is to the threshold, to alpha, the more I think, okay, maybe I could have not rejected. So the smaller the p-value, the better the rejection of the null hypothesis. And don't confuse P and alpha. Alpha is a test characteristic. I can say each of you can go and do a 5% level statistical test, but you will all have a different P because the P value depends on the observed value, which you will each get in your sample. So each value is different. So then we can talk with the last thing we need to talk about is the types of error. So when you do a test, there's always the population, the unknown reality, where either the null hypothesis is true or it's false. And here we have the decision following the test based on the sample. We either reject the null hypothesis or we do not. But here, when we do a test, we never know what is really happening in the population. So sometimes we reject the null hypothesis, whereas it's true. So this is a type 1 error, and the risk, the probability of the type 1 error is alpha. And if we do not reject the null hypothesis, whereas it's false, then this is a type 2 error with a probability beta. And here we have, this is not an error. If you do not reject H0 and it's true, that's 1 minus alpha. If you reject H0 and it's false, that's power, the statistical power of the test. So you have to remember that alpha has to be chosen a priori. So usually we choose 5%, but not always. What does 5% mean? It means that if the null hypothesis is true, 5% of the samples will erroneously lead to the conclusion reject H0. Okay, like the basketball team, means in a small number of cases, it will lead to the wrong answer, but in 95% of cases, you will get the right answer. And to calculate beta, you have to, that's a bit more complicated. So maybe I won't talk about that today. What I'd like us to do, so just what you need to remember about alpha and beta is that they vary in opposite directions. So both alpha and beta should be as small as possible, but unfortunately, if alpha increases, then if alpha increases, beta decreases, and if beta increases, alpha increases. So they go in opposite directions. So that's what makes it complicated. So what I would like you to do is to do a woo club. You know woo club? Yes, we are so excited. So, attendez. Donc, vous prenez votre téléphone. Donc, vous faites le...
Allez.
Ça marche ou pas? Does it work? Good. So, if everyone's ready, I get okay. On Zoom, can you see the Woo Club? Zoom, yeah? Voilà, don't start putting fire. Oh non, d'aller monter là-bas. Right, so, donc, si vous pensez, alors, it's written in French, est-ce que, does someone want me to read the questions in English or can everyone understand the questions written in French? I don't mind reading the questions in English. Okay, so I will read the questions in English for you. And you need to, okay, so you can start answering the questions. If you think it is true, you press on it. If you think it's false, you don't select it, okay? So true, for instance, if you think A, C, and D are true, you select A, C, and D, okay? And otherwise, you don't select. So I will read out the questions for those who are on the Zoom. So just a minute. So first question, the hypotheses of statistical tests. S'il vous plaît, faites pas trop de bruit parce que moi je lis au nom. Hypotheses of statistical tests concern the exact and unknown parameters in the population from which the samples are drawn. That's A. True or false. If you think it's true, you click it. If you don't click it. B. In order to do statistical tests, we need to calculate the test statistic based on the exact parameters from the population. C. Test statistics enable you to conclude concerning the properties of the observed parameters in the sample. C. Test statistics, statistical tests enable you to conclude concerning the properties of the observed parameters in the sample. D. A test statistic. A test statistic enables you to determine with a percentage error whether the difference between two parameters, you can't see the words out. I'll put the words up Okay, can you see the root cup now? Can you see the root cup? Vous avez fini? Ben non, il y en a. Vous êtes 34, il en reste encore. Certains qui ont fait des travaux.
Il y a plusieurs. En fait, c'est plusieurs pour ça.
Oui, mais c'est. Non, mais c'est pas ça. Il y a 34 inscrits et 27 qui ont répondu. Bon, vous avez le droit aussi de faire au pif, hein? Attends, je sais pas qui c'est qui l'a fait.
J'ai faux le temps.
Okay, so donc pour la première série, comment faire comme ça? Bam. It seems most of you were right, which is good. So I must be an amazing teacher. So I will just comment on the answers in case some of you got it wrong. So first question, the hypothesis of test statistics concern the exact parameters. That is true. In order to do test statistics, you calculate the test, in order to do statistical tests, you calculate the test statistics based on the exact parameters in the population. That's false. You use the observed parameters in the sample, since those in the population are unknown. And C, the test statistics enable you to conclude concerning the properties of the observed parameters in the sample. That's false because the conclusion always concerns the population, okay? And D, that is the definition of a test, okay, which enables you to determine whether the observed difference is due to sampling distribution or to a real difference. And the alternative hypothesis of a test can be bilateral, both sides, différent, or unilateral, okay? I can put those up on Moodle as well. So this was just, when I put it on, these are the bits of the course which answer the questions, but you can find the answers in the course. Right, next question, so of the week class.
Yes.
So next question.
Yes.
Off you go. So, is that working? No. Okay, I still have a few people who haven't answered. Is that because you're not listening or you don't know? You can look at les diapos. Vous pouvez regarder les diapos pour répondre si vous voulez. Hein. So you all seem to be agreeing, and you are right. The correct answers are B, D, and E. So if we look at this, Marche plus, merci, marche plus. Bon, since you seem to, I can't. No, we'll just keep going with the recap because it's nearly time to stop anyway. So next question. You can check all the answers. I will put the answers up on Moodle and you can check in the list. Next question.
Ah, si, ça y est.
Right, come on, there's only a few more minutes left. Have you finished? So. Has everyone answered this one too? So this time. So this is something you will need to look at a bit more, but it was at the end of the lesson and I will put up the correction. So there's just 2 more questions and then you can leave. So next question.
J'ai plein de sang. La manière dont d'accord.
Alors après, si vous vous basez sur les réponses des autres pour répondre, vous voyez comme sur la dernière, ça marche pas très bien. Ça peut marcher bien, au début ça avait l'air de pas mal marcher, mais là plus trop quoi.
La vie, c'est vibrer.
Ok, donc, dernière question. Et dernière question.
Ils ont relancé un petit peu. Il y a
C'est bon? Alors. Sur les deux derniers. Donc, je pense que beaucoup se sont trompés sur le D et le E, il me semble. Le risque d'erreur correspond au risque de ne pas rejeter l'hypothèse nulle alors qu'elle est fausse. Ça, il faut aller regarder sur les tableaux là. Alpha, c'est ne pas rejeter le risque alpha, c'est rejeter l'hypothèse nulle alors qu'elle est vraie. C'est pas ça. Et toute chose étant égale par ailleurs, lorsque alpha augmente, la puissance augmente, c'est vrai. Puisqu'en fait, quand alpha augmente, bêta diminue, et la puissance, c'est 1 moins bêta. Donc, ça augmente. Et le dernier critère, donc c'est l'avant-dernier, c'est là. Ici, lorsque l'hypothèse, je ne sais plus ce qu'il y avait comme erreur, oui, là il y en a beaucoup qui ont mis, c'est que le risque d'erreur est toujours fixé à 5%, non, c'est pas vrai, c'est souvent 5%, mais pas toujours. Et ici, lorsque l'hypothèse nulle n'est pas rejetée, cela signifie que la différence observée entre les paramètres est due à une vraie différence. Alors, ça pourrait souvent vouloir dire ça, mais il ne faut pas oublier qu'il y a aussi la possibilité qu'on n'ait pas mis en évidence de différences significatives, c'est-à-dire qu'on n'ait pas assez de puissance statistique pour montrer une vraie différence. Donc, il faut faire attention à ça, mais on en reparlera. Et en dernier, la seule qui était fausse, c'était celle-ci. S'il vous plaît, encore quelques secondes d'attention. La seule qui était fausse, c'était que le degré de signification, il change à chaque échantillon, puisque le petit p, il dépend de la valeur observée. C'est la probabilité d'être supérieure à la valeur observée. Donc, je vous mettrai ça en ligne, de toute façon, avec les corrections. Et à chaque fois, après, les diapos, c'est des extraits du coup qui répondent aux questions. Donc, voilà, c'est ça.